Transmission lines, single stub matching problems, series on transmission line theory, lecture number 3.31. Single stub matching technique is a simple technique used to match load to line using a short piece of lossless transmission line. In the present session, we focus on problems which involve short-circuited stubs, open-circuited stubs, real loads, and complex loads too. As first problem, example 1, we consider a lossless line, 100 megahertz lossless line with a dielectric constant 2.1, mu r equal to 1, that is non-magnetic. It is to be matched to its load by means of a short-circuited stub. Assuming Z0S represents characteristic impedance of the stub. It is equal to Z0. Z0 is characteristic impedance of the main line. Find the stub position closest to the load ds and its shortest length ls so that match is achieved when the line's characteristic and load impedances are A. Z0 is 50 ohms, ZL is 100 ohms. B. Z0 is 100 ohms, ZL is 50 ohms. Work out the design when open circuited stubs are used instead of short circuited ones. Now, solution process. First, we have to find out wave velocity. Wave velocity is c by root epsilon r mu r. Substituting the given data, one can find it is equal to 2.07 into 10 power 8 meters per second. The wavelength, which is ratio of wave velocity to frequency, then becomes 2.07 into 10 power 10 by 100 into 10 power 6 equal to 207 cm. Now, A. The distance of the stub ds from the load end is ds is lambda by 2 pi tan inverse square root of zl by z0. Substituting, lambda is known to us, zl is given, z0 is also given. Substitution using calculator, one can find ds as 31.47 cm. In the present case, zl is more than z0. Therefore, stub length is lambda by 2 pi tan inverse square root of zl z0 by zl minus z0. Substitution and using calculator, it can be found equal to 31.47 cm. Now we consider B bit. The distance of stub ds from the load end is ds is lambda by 2 pi tan inverse zl by z0. It gives 20.28. This formula is same as the formula which we used in case of A. Now in B, ZL is less than Z0. In A, ZL is more than Z0. Now here it is less than Z0. So LS is lambda by 2 pi, pi plus tan inverse square root of ZL Z0 by ZL minus Z0. Substitution results in a length 72.04 cm. So these are the distances of the stub, lengths of the stub in A and B. With open circuited stub, the distance ds remains the same. Length of the stub ls, however, changes, and as lambda by 4 is 51.75 cm, the length is 31.47 plus 51.75 in case of A. In case of B, it is 72.04 minus 51.75, that is 20.29 cm. Note here we have to consider impedance periodicity of the line. We have to consider impedance periodicity in pi and all that. Another problem. A lossless line is to be matched to a load by means of short-circuited stub. Assuming Z0S, that is characteristic impedance of the stub, equal to 75 ohms. Find stub position closest to the load ds and its shortest length ls so that match is achieved when lines ci and load impedances are main line characteristic impedance. Main line characteristic impedance is 100 ohms, load is 150 ohms in one case. In the second case, it is 150 and 100 respectively. Now, this problem is different from the previous problem in the characteristic impedance of stub. There it is, characteristic impedance of stub is same as the characteristic impedance of the main line, but in the example 2, in the present problem, these two are different. Now, the solution A. The distance of the stub ds is lambda by 2 pi tan inverse zl by z0. ZL is known, Z0 is also known, so it becomes 0.14 lambda. In case A, Z0 is less than ZL. Therefore, the formula for LS is lambda by 2 pi tan inverse Z0 by Z0 is square root of ZL Z0 by ZL minus Z0. So substitution. This part, it takes care of different characteristic impedances. So ultimately what we get is 0.20 lambda. B, the distance of stub ds, of course the formula remains the same, lambda by 2 pi tan inverse ZL by Z0. Substitution results in 0.11 lambda. In this case, Z0 is more than ZL. In the previous case, it is less, now it is more. So the formula is pi you have to use. And of course, Z0 by ZL, Z0 by Z0s takes care of different characteristic impedances of the stub and main line. Substitution results in a length 0.28 lambda. Another problem we consider. The difference between this problem, example 3, and the previous two problems is there the load is real. Here the load is complex. So the procedure, the calculation, the formulas, they are slightly different. A 50 ohm lossless line is to be matched to a complex impedance load by means of a short-circuited stub. Given that stubs are made from main line and complex impedance load ZL is equal to 30.30 minus J40 ohms. Determine the stub position closest to the load and its length so that match is obtained. Solution. Given Z0 is 50 ohms, ZL is 30 minus J40 ohms. Now gamma L. What is gamma L? It is reflection quotient over the load. It can be computed ZL minus Z0 by ZL plus Z0. It results in 0.5 with angle minus 1.57. This is radians. Magnitude of quotient is of course 0.5. Phase is minus 1.57. The susceptance of the stub is plus or minus B. B equal to plus or minus 2 gamma L by square root of 1 minus gamma L whole square. It gives plus or minus 1.155. Distance of stub from load is computed using this length is somewhat lengthy complex formula. ds equal to lambda by 4 pi minus 1.57 minus or plus pi by 2 minus or plus tan inverse 1.154 by 2 minus 2n pi. See, two signs are there. Minus, if you take upper sign, we get one value. If you take plus sign, we get lower sign, we get another value. So a little bit of manipulation, somewhat complex manipulation, somewhat confusing too. We get minus 0.292 minus 0.5 lambda for B more than 0. For B less than 0, it is 0.042 minus 0.5 lambda. Here the appropriate values for n are minus 1 when B more than 0 and 0 for less than 0. N value to n is given appropriately. These are the appropriate values. It results in ds equal to 0.208 lambda for B more than 0. For B less than 0, it is 0.042 lambda. The length of the stub for such case is, it is lambda S is lambda by 2 pi pi minus tan inverse 1 by 1.154. Now it becomes 0.386 lambda for B more than 0. For B less than 0, using the formula shown here, it can be computed as 0.1136 lambda. Closest position of the stub and corresponding length of its corresponding length, they are 0.041 lambda and 0.1136 lambda. You can see out of these two, the smallest one is lower one, 0.042 or 0.041, and it corresponds to B less than 0. For B less than 0, of course, length is 0.1136. Now another problem we consider. A 50 ohm 0.5 GHz transmission line having wave velocity V equal to 1.5 into 10 power 8 meters per second is terminated on an unknown impedance. It is found that VSWR is 4 over the line and first minimum is formed at 2 centimeters from the load end. Design a single stub impedance matching for the given conditions. The solution procedure, it is like this. Wavelength corresponding to 1 GHz assuming wave velocity equal to free space velocity is 30 cm. Lambda is V by F, frequency is given 0.5 gigahertz. So lambda is 30 cm. To find the distance and length of the stub, it requires the magnitude of RC and angle of RC over the load. These two parameters can be obtained from the given data as follows. Gamma L, magnitude of reflection coefficient over the load. It can be found from SWR. SWR minus 1 by SWR plus 1. SWR is given as 4. So gamma L is 0.6. Now theta L, reflection coefficient angle over the load is, it can be obtained from this relation to beta D minimum minus pi. So beta, lambda is known, so beta is known. D minimum is set, it is 2 centimeters. So substituting these values, theta L can be found as 0.73 pi radians. Magnitude of the quotient and its phase are now available. Now the susceptance of the stub can be found. Susceptance of the stub. V is plus or minus 2 gamma L by square root of 1 minus gamma L square. Substitution gives plus or minus 1.5. Now distance of the stub from the load is ds. This formula, it is same as what we used in the previous problem. Here two signs are there. Minus is there, plus is there at two places. If you consider upper sign, it results one quantity. If you consider bottom sign, another quantity. Now substitution and a little bit of computation manipulation results in one value for ds for beta more than 0, for beta less than 0, another expression. Now appropriate integer values are to be selected for n. Appropriate value is minus 1. Here appropriate value means something which gives positive and less than lambda by 2. That is appropriate. So ds with n equal to minus is 4.23 cm for b more than 0. It is 14.82 cm for b less than 0. Out of these two, this is the 4.23 is the smaller one. So smallest distance at which stub can be connected becomes 4.23 cm. Anyway, now the length of the stub can be computed as using this formula. Lambda by 2 pi, pi minus tan inverse 1 by 1.5 for b more than 0, another formula for b less than 0. Substitution results in 12.19 cm for b more than 0, 2.81 cm for b less than 0. But our requirement is we want to connect the stub at the smallest possible distance from the load. So it is 4.23 is the desired location, and it happens for b more than 0. But for b more than 0, length of the stub is 12.19 cm. So the solution to this problem is a stub whose length is 12.19 cm. It has to be connected at a distance of 4.23 cm from the load to the main line. These are some of the problems, solution procedures for those problems which I want to share with you.